Hello, everyone, and welcome to today's webinar, GPU Security in Practice, a Neocloud Provider's Approach. My name is Melissa Russell, and I'll be the host for today's session. Before we get started, I just wanted to go over a few housekeeping items. We are recording this session, and we will make a link to the recording as well as a link to the slides available probably in the next day or so. If at any time during the session you have any questions, please go ahead and throw them into the Q&A. Depending on the question, we might take it in real time or save a little bit of time at the end. At this time, I'd like to go ahead and turn it over to our speakers. Chase, take it away.
Thanks, Melissa. Awesome to be here. Thank you, everybody, for joining. Good morning, good afternoon, good night, depending where you are. My name is Chase Snyder. I'm in the product organization here at Eclipsium, and I'm excited to be presenting about a real live use case, how an actual Neocloud is using Eclipsium to secure their AI data center, and also a little bit more about the broader AI data center risk landscape out there. And with me is the esteemed Wes Dobry, who has many decades of experience in engineering. He's one of our global engineering leaders here at Eclipsium and has a lot of direct exposure to how folks are securing their environments. Wes, if you want to say a little more to introduce yourself, and then we can dive right in.
Appreciate it. Thanks, Chase. Now, the only thing I'll say is the several decades makes me feel a little old there. So thanks for that.
Just want to set you up with a strong foundation as a credible source. You look great, Wes. I couldn't do this without Wes. I really couldn't. But yeah, so the way we're going to do this is we're going to sort of start at a high level, talk about the overall cyber risk landscape, why securing GPUs and AI data centers is different than securing other, high performance compute environments and enterprise compute environments, and then get into a specific sort of ticking time bomb that exists in the cybersecurity risk landscape for AI data centers specifically. And we'll talk about how one Neocloud is preventing that or is mitigating that risk and getting out ahead of it. And we're going to keep it pretty conversational. So we'll talk a little bit about the topic. Wes and I will toss the ball back and forth a little bit. We would love to take questions from the audience. As you feel so led, pop them in the Q&A and we'll take them at the time or at the end, just depending on sort of how it fits in. So to start, we're going to talk about some mega trends impacting AI infrastructure security. We've got four listed on here. One is just massive investment. We've seen $1 trillion or so of investment committed to building out AI data centers specifically in 2025 so far. It could be even higher now. The stories, the disclosures of new investment come out so fast, it's honestly difficult to track. So huge amount of money and rapid build outs. That money, it's an investment. They want to see a return. The people that are taking that money on are trying to build AI data centers quickly. And so they are buying up land and power and GPUs and cooling capability and trying to do these projects really quickly. And that drives supply chain constraints. You can't build an AI data center unless you have the land and the power contracts, the cooling capabilities, and the GPUs, the actual hardware and the networking gear that you need to put it all together. Unfortunately, because there's so much competition, there's kind of a gold rush around all that. It's constraining the supply chain. It's driving up competition and prices for those things. And it's kind of driving down the focus on cybersecurity, reducing the sort of mental budget and monetary budget for security stuff in the face of those other critical requirements. And on top of all of that, AI data centers are being framed as critical infrastructure. So the narrative around these things, here's the CEO of CoreWeave, Michael Intrater. CoreWeave is one of the major neo clouds, very successful, IPO'd recently, saying, "We are standing at a pivotal moment where AI is transforming industries and reshaping innovation. Yes, it's a race to the top. We're racing to build the backbone of tomorrow's global economy and safeguard our national security in the process." So AI data centers are being positioned as this critical infrastructure component, not just by CoreWeave. Here's Jensen Huang, the co-founder of NVIDIA that you may have heard of, saying we're not a technology company only, we are an AI infrastructure company. So all of these sort of massive tidal movements that are happening are affecting the cybersecurity risk landscape. When you're a piece of critical infrastructure with a ton of money getting invested and security kind of on the back burner because you need to build out the data center and get it operational quickly, you have a target on your back by nation state APTs, by hacktivists looking to send a message, by financially motivated ransomware gangs. All of these people are looking at this with dollar signs in their eyes because these things are a ripe target for cyber attacks. And so we are going to talk about the sort of security concerns at each level, but particularly at the hardware and sort of data center level of AI infrastructure. I'm going to pause for a second because I feel like I've been talking. I need to take a breath and take a sip. Wes, what's your take on the overall risk landscape here? These mega trends driving risk for these AI data center buildouts. Like, where do we stand? What are you seeing in the field? You engage with people who are managing these enormous environments. Like, what's the general tone out there around cybersecurity and AI infrastructure?
Yeah, thanks, Chase. So, you identified a big part of this that when we look at these emerging use cases like AI that we see, that there's a lot of idiosyncrasies for how quickly the companies are transitioning, they're moving, they're adopting these technologies, and that in itself has some inherent risks. You kind of identified it that we still have to do our foundational controls in this infrastructure to reduce the risk as much as possible. But we get things to like targeting, additional targeting from sophisticated threat actors. We also end up in a very unique scenario where we're also implementing technologies that are starting to be at the forefront for researchers too. So this also entails that the landscape itself from a threat perspective is shifting very rapidly. And we talk about a little bit later as we go on too. But not only is this a shifting landscape for how we implement these technologies, deliver these technologies, secure these technologies, we're also in a very fluid scenario where the technologies themselves are also getting learned about where what the risk and threat vectors are within them. We're also learning as an industry and as a whole too.
Yeah, the ground is shifting under our feet, security wise, and just sort of the overall global technology infrastructure scenario. And when we talk about security in the context of I think usually where people's minds immediately go is like model security, model poisoning, data poisoning. It's sort of at the software level. Like your people are trying to do prompt injection to get the chat apps to say things they're not supposed to say, or people are worried that there's been tainted data introduced that introduces a bias into the models. Not a lot of discussion about the hardware level infrastructure. Not as it's not as user facing. Like users aren't thinking about the fact there's a giant GPU farms feeding them their ChatGPT responses. It's not something that a lot of people are having to pay attention to. But when you're building out an AI data center and you're buying just millions, billions of dollars worth of these GPUs and the associated networking and hardware and compute, all of that stuff, that is also an attack surface. Everything, all of the other things, the applications and the models runs on the hardware. And so if the hardware becomes compromised, it can subvert any sort of security mechanisms that you have deployed anywhere above that. It's the foundation of it, of the AI infrastructure. And so that's where we are kind of focusing. And AI in general takes a lot of hardware to run. You have these processes, you know, gathering the data, preparing the data to be used for training, doing the actual model training, tuning it. Inference is a whole other conversation. More tuning. There's all of these different processes that have to happen. And that uses a lot of different hardware. So on any given GPU server, in the hardware stack for an AI data center, you have CPUs, you have network cards, you have, the GPUs or the AI accelerators, you have storage, you have memory, you have embedded controllers, you have a BIOS, you have firmware. A lot of these different components that we've highlighted on the board here have their own software or firmware or operating system running on them. That's not necessarily something that the manufacturer of the overall board created. So there's this getting back into the supply chain complexity. Even at the board and the chip and the firmware level, there's this supply chain where every step of it reduces the amount of visibility and accountability that the end person who's building the data center, the end company or the end user, loses visibility and accountability. It's very difficult to maintain that across such a complex supply chain, and firmware often just gets left out. So for this discussion, we're going to talk about specifically baseboard management controllers because there's been an overall arc of cybersecurity investigation into these things. They're interesting for several reasons. But there's also been some really recent disclosures that like radically upped the risk profile associated with baseboard management controllers. I know I'm going to butcher this part, so I want to ask Wes to give us like a quick hit on what a BMC is and why it's meaningful to the security posture of AI infrastructure.
Yeah. Yeah. So a BMC is, as Chase said, is a baseboard management controller and is an out-of-band management component for effectively accessing your server hardware and managing it both locally as well as at scale. And ultimately, this is an independent machine that's built into the motherboard with its own hardware resources, running its own unmanaged operating system. Now, I mean, these devices typically take the standard approaches where they're running effectively hardened application operating systems or appliance operating systems on them. They're typically Linux based, and they're typically using relatively decent security controls within them. But the challenge with this and the BMCs specifically are the level of access that they have to the hardware. They have a direct connection to the system's memory, the system's serial peripheral interface, direct communication to the processor, as well as they do things like have network interfaces that ride within the corporate networks too. So they are, in effect, their own entire computer, their own entire entity, and need to be treated as such because of the attack surface alone for them.
That was perfect. Thanks, Wes. Yeah. So there's a computer inside your computer. And in an enterprise, when you have a computer in the enterprise, you install security stuff on it. Put an EDR agent, put some vulnerability management on there. People, you can't do that on the BMC. You can't install an EDR on the BMC. So it's like there's thousands or tens of thousands of computers inside your environment that you do not have the same security uh, measures taken against. And okay, so here's a rough timeline of BMC vulnerabilities. Back in 2013, it was disclosed that BMCs, I mean, okay, it wasn't disclosed that they used the IPMI protocol. That's just what they have used since the protocol was released in the early 2000s. But there's a vulnerability baked into the protocol, a timing oracle slash hash leak that was disclosed in 2013 that cannot be patched. If you use the protocol to spec, you have this vulnerability. And so you have to have compensating controls around that. Come 2019, and we'll go a little deeper on some of these later, but the basic timeline is over several years, there have been new BMC vulnerabilities, including specifically affecting data centers that have been disclosed. NVIDIA published some great research about over a dozen vulnerabilities in BMCs that they thought might affect AI data centers with NVIDIA devices in them. And then in 2025, the first baseboard management controller vulnerability was added to the CISA known exploited vulnerabilities catalog, which means that it was seen in the wild being actually used. So it went from this sort of increasing volume of known potential exploits or vulnerabilities, but we hadn't actually seen them being attacked, to, okay, people are using these attacks out in the wild. And that essentially to me means that BMCs are sort of the canary in the coal mine for AI data centers. If you think about that map of hardware, any one of those little chips has the potential to be targeted. So for a deeper dive into the 2019 one from that timeline, Eclipsium did some research that showed that vulnerabilities in a baseboard management controller, specifically in some IBM hardware, would allow a customer of a cloud provider that had those BMCs in their cloud, in their data center that they were running their cloud out of, to leave a backdoor on a server in that data center. And something that was noted in the research at the time is that data centers were missing the sanitization of firmware components, leaving customers vulnerable to attack. And what that means is that the shared resources, the hardware that gets used by different customers over time in the cloud provider's data center was not getting totally sanitized and restored to a secure state between customers. So one customer would say like, hey, I need some cloud resources for whatever purpose. They'd use it for a little while. They'd like change their configurations. They're doing this on a bare metal basis, so they have deep access to how that hardware is set up and configured. And then they finish their use case. They're like, okay, I don't need this anymore. Um, and the data center has to reclaim that hardware and reinstate it to a gold image, sanitize it to let the next customer do it. And they were doing that, but not all the way down at that component chip firmware level. And the BMC turned out to be a potential attack vector in that case. We talked about NVIDIA having put out some BMC security research, and this has a really critical tie into that supply chain challenge is that, so this research, I think came out in 2023, explored 18 vulnerabilities in BMCs and had 9 proof of concept exploits associated with it. And the researchers stated in the research that in spite of BMCs being a critical component to the overall platform, NVIDIA did not have direct access to the source code of the firmware on those BMCs. That means they had a supplier. The supplier provided the firmware on the BMC that went into the NVIDIA stuff that was critical component to the platform. And NVIDIA themselves did not have visibility into the BMC firmware. And they were pointing out all these vulnerabilities in that code. So it introduced challenges into the research. And they are, they're the best at what they do. So if these researchers had a difficult time investigating that source code, how is the security operations folks at an AI data center that's trying to protect themselves against BMC attacks going to do it? And then we talked about 2025, seeing the first BMC vulnerability on the KEV. So when I say that BMC vulnerabilities are the canary in the coal mine, what I mean is they've been building up more and more of a backlog of vulnerabilities and potential risks. And now we are seeing attackers start to use them. And probably the reason for that is that they're very tempting because the amount of control and access that a BMC has over the hardware that it's installed in is very high. And they're hard to monitor. It's hard to see inside of them and see what they're doing. And so it's easy to maintain persistence, even if the power goes off in the hardware that the BMC is managing, even if the OS is not accessible, the BMC can still operate. Even if you reinstall the operating system, you restart the whole thing. If an attacker has a hook in that BMC to do their command and control or do whatever they're trying to do, you can't get them out with those sort of normal remediation steps. Very difficult to mitigate and to detect this kind of thing.
Yeah, and I'd like to double click on this specific CVE a little further. This CVE, as you guys see on the screen here, is a remotely accessible authentication bypass. So the only thing the attacker needed to do was be able to reach the Redfish interface on that BMC. Now, most organizations, as part of a best practice, isolate BMCs or any sort of out-of-band management of servers into typically its own VLAN or its own secured network. But not everyone does that. Like there's literally BMCs that are out on, like you can find them on Shodan and they're accessible over the internet, for example. And in assessments that I've done, I've found organizations that don't realize that in some configurations, the BMC will ride on the primary network interface as a secondary NIC. And so you plug in one, RJ45 into the management or the primary NIC, and suddenly the BMC pulls an IP address on the public network segment too, or the host network segment itself. So this ultimately means that if anybody has access to the network and can scan for the system, which is easy to identify through a banner identification, they can go and do an unauthenticated access to this device. Now, where this gets real crazy is that most of these BMCs have a driver, like an IPMI driver within the OS, that allows you to do things like mount a CD-ROM or mount a USB disk image into the OS itself. And so, as you can imagine, you get access to the BMC, and not only do you have capability to do things like hit the power button, initiate a disk wipe, or reboot the host, you also have the capability to go and do things like remote session into the OS itself or add a USB drive or something like that to it. So you have opportunity to move from the BMC into that host operating system. Now, you also have the opportunity once you get into the BMC to launch other exploits against it to get root access into that BMC itself, which then gives you opportunity for lateral movement to other BMCs on that same network segment. So if the organization isn't isolating BMCs on things like PV LANs or doing host isolation, you now have lateral movement from BMC to BMC, even if that device is compromised from, some external source. So that's why I think that we see this on the CISA known exploited vulnerabilities list, because this gives them easy access to it and gives them a very silent methodology to remain persistent and move across an entire data center and maintain control.
Sounds pretty good. If I was an attacker, those all sound like things I would want. So, yeah, that was a great summary of why a BMC access would be so devastating, A, and appealing for an attacker, B. So the overall message here is that BMC attacks, it's not the only thing that is a hardware level infrastructure risk to AI data centers, but it is something that is coming up quickly, and I'm expecting us to see more and more uh, news stories of exploits and vulnerabilities in BMCs. Hopefully nothing too devastating, but the possibility is there. But BMCs are not the only hardware that's at risk. Just one example, just recently, a variant of the Rowhammer exploit was found to be viable to use against NVIDIA GPUs as well. So this is a hardware level vulnerability that affects the physical behavior of DRAM memory and would potentially allow a malicious GPU user to tamper with another user's data. And something that was noted that I think is really critical in the research that disclosed this potential vulnerability is that GPUs often lack parity checks and instruction level access control, leaving GPU memory integrity exposed to low level fault injection attacks. This is a little bit of what I hinted at earlier, that GPUs are different. They went through this sort of trajectory, right? GPUs came out for graphics, like they were great for video games and improved video performance. And then it turned out that the same sort of vector processing that was great for graphics was great for Bitcoin mining. And so GPUs had this like boom in that realm. And then it turned out that that same sort of vector processing that's good for Bitcoin mining also really great for AI. And so the original sort of design goals for GPUs, they've evolved a lot in what they're being used for, but they're still ultimately fairly early in their journey as a sort of hardware component compared to like CPU and other stuff that we've had around for a lot longer. And they just haven't had the sort of battle testing in the field for against cybersecurity attacks. And they haven't, because of their different performance requirements and different needs that they fulfill, they don't have the same security profile. And the security stuff hasn't quite, evolved yet. And so trusted execution, confidential computing, having all of that stuff actually work in an environment that's primarily AI accelerators or GPUs requires a different security approach, and one that's not quite, that's still in its use, still evolving. And that's something that we're working on helping some AI data centers with.
So
So
can we go back to that for me,
yeah,
Chase?
absolutely.
Yeah, so I want to give a little more details into what this is and why this impacts our customers or AI folks as a whole. So you may or may not know what a rowhammer exploit is, and it exploits a characteristic of DRAM where effectively if you write things to different rows and repeatedly hit it, you can actually cause bit flips in adjacent rows within the memory itself. And that's kind of why it's called a row hammer attack. And the idea is that you do this a whole bunch of times, and you can eventually go and start to corrupt the data that's adjacent to where you're writing. And what this looks like is this is ultimately the reason that we started seeing things like ECC memory on servers, error correcting memory on servers. Now the challenge is on GPUs. We have started to see some GPUs coming with ECC memory, but for the most part, and this goes back to the supply chain challenges of availability of GPUs that people or organizations have had to either buy lower level GPUs or what's available that may not have these kinds of controls like ECC memory on the boards, or they don't want to impact performance of the GPUs themselves, so they don't get the boards that have the performance degradation of having ECC memory. And now this means that if I, as an attacker, start to go and hammer the model in a way or execute things against that GPU in a way that causes a lot of bit flips, I can now tamper other users that are in adjacent memory segments, degrading their performance, their capabilities, their the model as a whole. So really, this is more of a scenario where if even as a part of a public service, if you're using any services that do direct access to GPUs, then they're likely susceptible to these kind of challenges that can impact other users on the system without any other operating system controls that can isolate.
Yeah, that was awesome. Thanks, Wes. Deeper dive into how the row hammer attacks work and why, yeah, it's different in GPUs. And that supply chain angle that you called out is interesting. I was not honestly thinking about that at this moment, that um, since the market is so tight and the demand is so high for those, some folks who are building out AI systems, maybe like even in their enterprise, just building out a cluster, are not buying the latest and greatest. They're getting whatever's out there, and they, might be a generation or two back on those security controls.
hmm Yeah, and this is absolutely something that we've seen in numerous of the Neoclouds at this point, where, availability of the latest generation devices is not acceptable or not available to them. So they've had to buy devices that don't have even things like integrity controls enabled. They may be the current family of chips that are available, but they might not have integrity controls available on them so that you can actually take integrity measurements of the firmware on that GPU itself. And this has actually caused scenarios where we have to tell them like, hey, there's no way to validate that this device isn't running malicious code on it now, or even that it's running what you're expecting on it. And this is 100% because the time to market to get them the services delivered is more important than either the security or the efficacy of the system as a whole.
Yeah, tale as old as time. Uh, but I think as we over time, we'll see enough more challenging incidents that hopefully security will become a higher priority. You That was a perfect segue into the topic of hardware integrity and trust for AI data centers, and essentially the importance of having those mechanisms of verifying the integrity of the hardware, verifying that that what you expect is running inside of that hardware at a deep level. And I'm going to have to plead the fifth on SPDM and ask Wes to talk a little bit through what SPDM is and just general other mechanisms for doing the hardware and firmware integrity validation, and then the value of doing that for an AI data center.
Yeah, so SPDM is a standard for gathering attestation information from the devices themselves. So this is effectively allowing the device to say, "Hi, here I am. Here's what I am, and here's what code I'm running on me." Now, I mean, this does result in you have to trust the device to do its attestation. But this is analogous to what we've seen with things like TPM and doing TPM based attestation. SPDM is just slightly different way to do it, and it doesn't have a specific hardware enclave that stores those measurements within them. But what this allows organizations to do is regularly collect that attestation information to validate if the device has changed, if there's anything on it that's different than what's expected, and to set that baseline. So as Chase was talking about earlier, like as a cloud customer goes from one customer to another, there needs to be something in there that validates that the system's at a baseline perspective. That's really where things like SPDM come in, where, excuse me, you can take measurements from the system itself. You can also take measurements from things like the GPU, and then you can go and carry that into things like kernel measurements, and then even into things like software measurements to make sure that device is at the level of trust and integrity that you're expecting of it. And this is really a key and critical part that building towards these types of solutions, you have to go and take zero trust really isn't the right word because a lot of people align zero trust with things like network access. This is actually hardware trust and validating that the hardware and the layers below the OS and everything that's delivering that hardware resource to the operating system can actually be trustworthy. And that's where things like SPDM and TPM attestation and even things like measured boot come into play to ensure that that device is what it says it is running code that's trusted and that no one has done any changes against that could be considered malicious or nefarious.
Awesome. And that is a perfect tee up to talking about how Eclipsium verifies and validates hardware integrity. So I think we'll start at sort of an introductory level of how Eclipsium delivers these capabilities for all types of devices, and then we'll get into the specifics of a use case of one Neocloud that's using us for this scenario of needing to make sure that the bare metal shared infrastructure that they're using is secure, not only to protect their customers, but to protect themselves, both their reputation and the actual technology that they use to, run their business. Wes, you want to give this walkthrough of how Eclipsium delivers on these needs?
Yeah, no problem at all. So, if we go back to what I was just mentioning about device attestation, we're all used to using things like Secure Boot and TPMs on our endpoints and our servers traditionally. And the concept there is that it collects information about the state of the device's integrity. Eclipsium, we ultimately do the same thing, but we do it with a software-based approach with what we call a sensor. And part of what we do is actually extraction of the code that's running on those devices themselves, and then doing independent verification of it. So we're going to extract things like those integrity measurements and actually extracting things like the UEFI and EFI and bootloaders and all the way into things like the XROMs and VBIOSes of the GPU, PCRs from the TPM, all of these different things that run on the device. And then that's used as intelligence that we do an assessment of risk, threat, and trust against. So since we do things like extract UEFI from the system itself, we can actually run that through our engine where we start to look at it from a threats perspective. Or we can do things like generation of SBOM, FBOM, and HBOM. And those are software bill of materials, firmware bill of materials, and hardware bill of materials. And that could be fed into something like a CSCRM or Cyber Supply Chain Risk Management program so that you can identify if things match what you're expecting or if things have changed. So if I see something like a GPU version that's different on one GPU when I have 10,000 of them, that can identify where either something's changed, some kind of an indicator of an attack, or even in some situations, depending on what that change is, it can be an indicator of compromise that's discovered on that device.
So that's a great tee up for telling the story of how one of our actual customers is using us. And this is, a very simplified kind of timeline of it. But the fundamental risk that they sensed was that as they were very rapidly turning over bare metal GPU infrastructure between customers who were doing model training, more likely model training than inference, but it could really be either one. They realized that if it takes them a long time to take control back of that hardware and restore it to a golden state, that's time that they're not making money from those GPU hours. And there's there's a Bloomberg index ticker for the cost of a GPU hour now. Like this is a meaningful economic unit is how much it costs for an hour of GPU time. And it is super important given the amount of competition, including price competition between these neoclouds, for them to have this, money printer on all the time. They got to be they any amount of time that the customer doesn't have the infrastructure and isn't paying for the hours is taking away from the viability of the business of the neocloud. So they need to be able to restore it to secure state very quickly and turn it back over. But when a customer, leases GPU infrastructure on a bare metal basis, as we discussed, they get a lot of control over the configuration. In the Cloudborne situation, that was demonstrated to leave the door open for a customer to potentially introduce malware or a backdoor or like just an unintentional misconfiguration that would cause data to leak from one customer to the other, or otherwise pollute the usage of the subsequent customer. And so what we're doing is, fundamentally, customer finishes using the bare metal infrastructure. The Neocloud does the reclamation process to restore it to a gold image, and Eclipsium helps validate them, doing that deep, integrity validation and attestation checking to make sure that down to the firmware and like the NVRAM like level, these things have been restored to a secure state to assure that there has not been a backdoor or any risky misconfigurations introduced, doing that super quickly so that they can get it out to the next customers who are charging again for that stuff. That's the high level. Wes, I would love to hear any sort of more chewy, juicy details, especially stuff that would be relevant to our audience as far as like if you're thinking about how to secure your own AI infrastructure, your clusters in your enterprise, or you're thinking about using an AI data center, or you're already using them, what kind of security requirements do you have of them, and what kind of reassurances are they giving you that the infrastructure you lease from them is being secured at this level so that there's not a backdoor in the gear that you're accessing in that data center.
Yeah, and you kind of hit the nail on the head there of the approach for bringing things back to a known expected baseline, and that's ultimately going back to a state of trust of that device. And what you have up here on the screen is a perfect example of it, where whether there's a single validation or multiple validation steps that go through it, there's an aspect of validating that when customer A turns the equipment back over that system is restored back to a trusted state. And we're the control that validates that for that customer. And then the concept is that this is ultimately the approach of protecting against the threat vector of moving from one effectively customer instance and remaining persistent beyond after your workload has finished. The the second part of it is regular operational monitoring, and this is a scenario where a lot of the organizations that aren't leasing equipment or are building it themselves, where it comes into play, where regular validation of this kind of stuff ensures things like that devices are operationally the same, identification of drift within a piece of infrastructure. And this is, if you have a whole bunch of servers that should look exactly the same and one of them's a little different, these are the kinds of things that need to be called out and identified as to understand the why of it. This also goes into validation that things are what they should be against what manufacturers ship. So if you've got a system that has a vBIOS hash that's different than what NVIDIA shipped for that GPU version, GPU and driver and firmware version, then that's also something that you should at least know about and investigate inside of your environment. And all of this is ultimately to have a transparent approach to what's happening at a hardware and firmware layer, while also giving you operational controls to do this at scale.
We've got a question in the Q&A that I think makes sense here to take live, which is how often to carry out integrity checks and validation. And I'm guessing it depends on your environment. But Wes, when you engage with these customers, what's your recommendation of the cadence of this kind of validation?
Yep, it depends on your environment. Now, in all honesty, it's really going to be heavily dependent upon what the workloads are and at what stages those in those checks and validations can occur. In some situations, the expectation is that there's zero performance impact to it, so they can be carried out real time regularly, and that regularity could be, in some situations, daily, hourly, or even more frequent than that. Or in scenarios like SPDM kind of validations, they could be done, effectively almost continuously in some regards. In most cases, I find that there's a bit of a balance to only really checking at times of risk, like transition of customers, transitions of workloads, um, or something to validate against that use case, like during the deployment sequence and then regularly, like once a day as that system's ongoing. The other question that just came in, it says, is there a monitoring framework that is continually inspecting the infrastructure state for this type of vulnerability? And the answer is that is exactly where Eclipsium fits. Now, there are open source tools for doing some of this integrity verification against things like SPDM. But ultimately, to do it at scale and have a singular platform that does this and integrates with other things like security operations, that's exactly where Eclipsium fits in.
Awesome. Thanks, Wes. There's one
Mhm.
other question in here that's not exactly on um, this topic, but it's about do you have any examples of successful or attempted attacks against AI hardware or hardware components used to construct AI environments? And for that, I'm actually going to click back to the slide about the BMC vulnerability. So this is a real attack. When CISA puts something on the known exploited vulnerabilities catalog, that means that they have observed it in the wild. They often do not publish details about, they might not attribute the attack to a specific threat actor. They might not say who has been attacked or release more information about the tactics, techniques, and procedures. Usually, if those details are missing, it means that there's an ongoing investigation and they don't want to tip their hand too much about. So there's sort of a balancing act for disclosing that this is actively exploited so that organizations can adjust their risk profile towards it and say like, okay, if I have the BMC, the AMI mega rack versions here, I should go investigate them and get some compensating controls in place. So CISA wants to give people the heads up that they should shore up their security around this, but they might want to not want to disclose other details. So we don't know whether this is being used against AI data centers or not. But what we do know is that baseboard management controllers are in AI data centers. I believe that some BMCs that are in NVIDIA gear use AMI firmware. It may not be the exact versions. There's a lot of different versions, which introduces a lot of complexity into firmware security, is that it's often several layers back in the supply chain was like the provider that created the firmware, and they have a lot of different versions. And then sometimes those versions will get, modified or updated downstream by other users. So there's a lot of difficulty in attributing that and sort of tracing that across the supply chain. So yes and no to your question. This is a component that's in AI data centers for sure. And CISA is saying it's being actively attacked. Are the instances that are being attacked in AI data centers? That is yet to be disclosed, but I feel very confident that within the next year or so, we're going to see more BMC based attacks happening because it's just too valuable of a target for attackers to ignore. So I think this is just the beginning of what I would expect to be a sequence of disclosures about folks getting hacked through their BMCs. All right, I'll go back to our regularly scheduled programming. We have some good questions coming in. Please keep them coming. Thank you for that. Um, this is where we were talking about how this Neocloud works. We can dive in even deeper to how we do our analysis. We could also answer. I guess there's one more question here that I think is
Yeah.
worth talking to. Actually, Wes, you want to take this one?
Yeah. I actually will answer it as we go to the next slide. And the question is, can open source for checking the integrity of a device itself be compromised? And where do you draw the line on validating things? And the answer to that is absolutely. There is always the opportunity for supply chain attacks and something within an open source package to have some kind of an implant put into it at some modification added to it. And we saw that what was it, last year or the year before with the XZ package, where some threat actor made a manipulation to it that introduced a vulnerability in it. And that's absolutely something that could happen with the open source package of it. For things like SPDM and some of the other packages that validate TPM attestation. Now, the concept that I approach this with is just simply looking at the process as what provides me the most transparency and the ability to validate what it's actually doing. And in things like SPDM validations or attestations, I should say, the part of it is the only thing that you're getting is effectively a hash. And this hash doesn't actually tell you anything about that device or that binary or that BIOS on that system at all. And this is the same challenge that you see with organizations going through an implementation of cyber supply chain risk management programs. You can get things like SBOMs, and they give you great opportunity to identify known threats, but they don't actually tell you anything about why something should be trusted. And this is kind of a concept where we could literally have an entire day-long conversation about that whole piece of it, of how do you build reputation in something. And that's where when I look at what we do is we take a slightly different approach. That reputation check, the only thing that it does is it tells you something is known. And that doesn't tell you if it's trustworthy. It just tells you the desired or initial verification state of it. Now, if that's something that you trust, then cool. It's already great. You can mark it as known and move on and say that it's good. But if you don't know exactly what it is, that's where you have to do some extra legwork to identify the level of trust within that specific component itself. And that's where things like what we do with what we call automata comes in, where we don't just trust something like the hash. We try to get the actual binary itself and run it through software analysis techniques to then identify things like threats and risks and vulnerabilities and weaknesses within it. And that's where we use techniques like decompiling, disassembling, sandboxes, and others to identify known and unknown threats and heuristics. So ultimately, this goes into a hash only tells you a hash. It doesn't tell you anything related to trust. You still need to verify and build that trust in whatever you're running.
Fantastic answer. Perfect segue. Thank you for that question. Thank you all for all of these great questions. This is really leading to a richer discussion. It's always nice to hear what folks are curious about. That brings us essentially to talking about the overall hardware life cycle. So we've talked about supply chain a lot, and often I think when people talk about supply chain security in the context of cybersecurity, the first thing that a lot of people think of is exactly what that last question was touching on, which is like open source packages. There was the XZ compromise a year or two ago, and just this year, there's been a big disclosure of NPM, a node package manager, packages being compromised, and the idea of a malicious actor essentially issuing a pull request against those and getting some malicious code into an open source package, and then that being propagated out through the open source ecosystem yeah, that's very scary and real. But the same sort of risk can be introduced through non-open source, just private supply chains, which have a lot less transparency. Open source stuff tends to have a lot of eyes on it. There's especially for stuff like NPM, there's a big community that's contributing, that's watching it. All the diffs are public. It's and yet still stuff gets through. So imagine when you've got a vendor like AMI, not to pick on them, but the mega rack vulnerability we talked about was in the AMI stuff. They did a great job, responding to that and mitigating it, and disclosing it and everything. So props to them for handling it appropriately. We've got a vendor like them who is producing this, and then someone buys their chip and builds a board with it. And someone else buys that board and installs it in a server, and someone else buys that server and racks it and stacks it with a bunch of other stuff. You've got these layers and layers and layers. And if there's any sort of a vulnerability in there, the ability of the end user to mitigate that is very challenging. And the ability of them to hold any of those supply chain steps accountable for the security is very challenging too. And we're starting to see, both in the US and internationally, increasing regulation of hardware and software supply chains to where there was a recent act in the EU, the Cyber Resilience Act, that contained a lot of clauses around requiring software bills of materials, requiring any sort of digital element and all of its components, which would include chips and their firmware, to be included in an SBOM and to have vulnerability handling at every stage. So anybody who's bringing a digital product to market has some responsibility for the supply chain security of it. And in the US, there's been recent defense projects, the Golden Dome Missile Defense Project, And these AI data centers, memos are coming out of the Department of Defense and the Pentagon and various organizations very explicitly requiring supply chain security efforts, like providing a software bill of materials and maintaining a software bill of materials no matter where you are in the supply chain, as a member of the defense industrial base or any of these vendors that are participating at any point in that supply chain. So not only are attackers paying more attention to this sort of avenue of getting in, but defenders are starting to be required to shore up their defenses against threats introduced through the supply chain. So when we talk about securing the entire life cycle, what we really mean is knowing that the supply chain is opaque to you. Um, all right, we've got someone signing off. Thanks so much for joining. Really appreciate that. Everybody else, we'll keep going for a few more minutes. Keep bringing your questions if you want. But knowing that the supply chain is so opaque to you and difficult to secure, you basically need the ability to audit everything that comes into your environment at that deep level. Okay, you can't stop the vendor or the open source community from creating a vulnerability and sending it your way. But what you can do is deeply analyze everything that you get before you install it to make sure that either there's no vulnerabilities or you know the vulnerabilities ahead of time and you can establish compensating controls so that you can still use the stuff that you bought and want to use. And then you have to continuously monitor those things because new vulnerabilities get discovered all the time. And so even if when you onboard every device, every new piece of software and hardware and firmware, even if you make sure it's totally secure or compensated for at that time, a new 0 day could get disclosed the next day, and then you've got this 0 day throughout your environment. And what do you do about that? So continuous monitoring at that deep hardware and firmware level. And then when you decommission assets, it's important to have that visibility as well. It's the same use case as the AI data centers having to sanitize their devices before they lease them out to another organization. When a company gets rid of servers or network devices and routers or laptops, they have to sanitize that stuff. And if you're not sanitizing, data sanitizing those devices down to the firmware level, you could be leaking really critical information about your organization that whoever, picks that stuff up out of the dumpster or buys it on the gray market next could have access to really critical info about your environment. And we've actually got customers using us for this exact use case as well, where they'll scan their servers that they're about to decommission at this deep level so that instead of just sending them to be shredded and like recycled as metal, they can resell those with the confidence that their sensitive data has truly been eradicated down to the very deepest component level so that they can resell that stuff and recoup some of the costs. Because, again, partly due to the supply chain challenges that we're facing, secondary market, sort of aftermarket gear still has a lot of value and a lot of life left. And so big organizations with big budgets that are refreshing their gear every couple of years can make good money selling that stuff to organizations that don't need the latest and greatest and just can't buy it or afford it because of the supply chain constraints that exist right now. So paying attention to that entire device lifecycle from a security perspective is really vital. Okay, that was a long rant from me, but this is something I'm passionate about and something we're really focused on here at Eclipsium. Uh, Wes, what's your takes? Device lifecycle management, security lifecycle for AI data centers and beyond.
Yeah, so I always like to equate this to a story that's personal for me, and that's the things that I do at my own house. So, like when I get a nice new server or I get a new technology device, the first thing I do is I immediately rip the shrink wrap off of it and plug it into my wireless network or otherwise onboard that device. And this is one of those things where I look at it and I go, I did no validation that this device came from whatever manufacturer I purchased it from. Or in situations like, maybe I bought a used server from one of the server repurposers. And, the scenario is when I actually start taking a look at that device and I realize, I recently got a server, it was an HPE box, and it had like Dell NVMe drives in it, and then it had no name memory. And I'm like, whoa, this isn't what I actually ordered. And so like that's the first step is validating the trust in the equipment at that stage. Then it, of course, goes into that continuous monitoring throughout the life cycle to monitor for changes, risks, threats, any of those kinds of things. And then, like Chase mentioned, the decommissioning side is let's just make sure that things are in a known state before we do something where that device leaves our data centers, whether that's to go be recycled, resold, repurposed. Doesn't really matter, but the idea is that that thing should not bring any data, and that data could exist in areas outside of the hard disks or the solid state drives on it. So resetting firmware, resetting settings on the device, and ultimately getting that device to a known state that has no proprietary information on it is paramount.
100%. All right, we've got I'm going to call it more of a comment, but we can talk about it. We still have a couple minutes left. Love to keep the discussion going. It says, but the same is true for smartphones. The end user it's not feasible to do such a validation, and those devices are used on corporate networks too. Absolutely. Any sort of an endpoint that is connecting to a corporate network is a potential attack surface. And I mean, I think a lot of organizations have a pretty high awareness and level of concern about those kinds of user endpoints. And so they'll do device management and they'll, have users, if you're going to connect your phone to corporate networks, you have to install these security solutions on it. And a lot of those solutions just do not exist for the kind of, network and server and GPU infrastructure that we're talking about. So it's like, yes, the end user can't do the validation on the smartphone, but there's a bunch of security stuff. Like it's a known risk. It's not being ignored. A lot of the time, this kind of stuff, this like BMC level security, it's not being totally ignored, but it's not being innovated at the level that it would need to be to address attacker behavior innovations. I don't know. What's your take,
Yeah.
Wes?
Yeah, so Mike's question actually hits on a hot button topic for me, and that's effectively walled gardens in technology. This is a problem that extends beyond smartphones. It goes into IoT, it goes into some networking equipment. It goes into scenarios where manufacturers do not give us the capability to validate the integrity of these devices. And this is again a topic that we could spend an entire day talking about why this is bad for our technology ecosystem as a whole. Because the bare fundamentals is that we need the capability to transparently verify the integrity of a piece of equipment or test that that device is what it says it is. And things like smartphones are a perfect example of this, where they are a complete black box walled ecosystem where you don't have the capabilities of doing those validations and you have to trust the vendor. And trusting the vendor is fine and all when we have things like contractual controls, but when our operational mandates inside of our organizations is to protect our infrastructure at all costs, we can no longer just simply trust the vendor. We have to have additional controls to validate the equipment that we're using. And that is the mission that I'm on, is to get organizations and vendors to open up the capabilities to go beyond and verify everything from bottom to top, from hardware, firmware to operating system to software at a complete appreciable level so that you can have a transparent perspective on risk. And Mike just confirmed it goes way deeper than MDM or OS or any of that kind of stuff. This is a fundamental challenge that us as consumers of the equipment also need to demand from the manufacturers and the vendors of those, that their equipment provides a way to do these validations or verify these attestations on the devices. Rant
Yeah.
over.
No, it's a good rant. Yeah, the organization often when a vulnerability is disclosed in something like a firewall or a network router or whatever, the vendor's response, so it's like the vulnerability gets disclosed by a researcher, the vendor's response will be to say, if you deployed this appropriately as instructed in the manual, that vulnerability wouldn't be reachable. And so it's actually no risk to you. So they're basically saying, trust us, or like sort of punting back to the user, which is kind of icky to me. But fundamentally, the practice of not allowing that kind of visibility inside of the device while shipping things with these vulnerabilities and then saying, no, those vulnerabilities don't affect you if you install it right. It's like not everybody's going to install it right. There's sort of an accountability that's not there. And getting this capability that we're trying to provide to look in there yourself as deeply as possible is our way to try to help give back the control to those end organizations and say, we're not going to, we won't accept this gear from you that we know has this vulnerability that we discovered because we looked inside of it. We found this vulnerability in the hardware, and letting these companies hold their vendors accountable and also just keep themselves protected from that sort of opacity in the supply chain that has the potential to introduce vulnerabilities. Yeah, I'm curious how the EU CRA is going to go as well. We had a great blog post about it recently, very much tracking it closely. We are at time. This has been a great discussion. Wes, it is always a delight. You have so much great knowledge in your brain, and I love to talk with you about these things. And I'm so happy that everybody had these great questions as well. So we're going to sign off. I'll hand it over to Melissa to do the final sign off. Wes, thank you so much. Everybody who joined the webinar, thank you so much, and enjoy the rest of your day.
Thank you, everyone, for joining us. Thank you, Chase and Wes. Just wanted to remind everybody who had a couple questions, we did record the webinar, and we are going to make a copy of the recording as well as the slides available to you. You'll see a follow-up email from me. And now I hope to see you on our next webinar. We are shooting for October 16th, and just to give you a hint, it'll be about the F-bombs and S-bombs. So look forward to seeing you out there. Thanks, everyone.